Okay, so let me recall what I did in the previous. Let me check the sound first. Hello. Yeah. Okay. So what we did in the last video is so we did relativistic Worldline theory for a spin zero particle, and so we have this Worldline going from xi to xf, initial and final event, and it is parameterized by a parameter s, which is monotonically increasing. So we considered a quadratic action on the Worldline, which is given by 1 over alpha in integral ds 0 to 1 lambda inverse x dot square minus lambda mu square, where in the last video I took alpha to be 2. I'm keeping it free. It's a real positive parameter, real positive, and both lambda s and x s are one-dimensional, should be viewed as one-dimensional fields, and mu square is positive, real positive constant, real positive constant, and x dot square is equal to eta mu nu dx mu ds dx mu ds, and eta mu nu is mostly positive. Then we showed that lambda extremized action is given by s prime of x. Lambda has been extremized, and that's given by 2 nu over alpha integral ds 0 to 1 square root minus x dot square. And this s prime with further extremization will produce the correct classical equations portion. So further extremization produces expected classical equations of motion, which is given by d tau over ds equal to 0 for massless, and d2 x mu d tau to equal to 0 for massive. So value of mass, we should remember value of mass cannot be determined in classical free theory. And so d tau square is the proper time, which is minus eta mu dx nu, and S is equal to S of tau is an invertible monotonically increasing function, invertible function monotonically increasing with tau. Since nu is an overall factor, nu is an overall factor in action, this means that no role, it doesn't play any role, no role classically, as I mentioned before, but quantum mechanical effects are more suppressed for larger values of nu, and this indicates that nu could be proportional to the mass of the particle. Okay, we shall now focus on computing the propagator explicitly. So explicit computation of propagator. So if I is equal to integral dx from I to f, then integral d lambda, this d lambda is also a path integral, and then e to the power I over h bar is x comma lambda. Now there is a further complication in this particular example that I want to explain now, which was not present earlier, which is that this is not the definition of, this cannot be the definition of the propagator. Rather, we should have a modification here, which is this. And this V is called the gauge volume. We should divide by the gauge volume, and let me explain what we mean by gauge volume and why we should divide it by the entire path integral. Okay, so so let me explain V on the gauge volume. Okay, first let me explain what a physical symmetry is. So the usual symmetries that we have studied so far I'm referring that to physical symmetries because of the following reason. For example, take an example of hydrogen atom. It has a spherically symmetric potential V of R. So the Hamiltonian is invariant potential, or the Hamiltonian is invariant under the symmetry transformation is R vector is rotated by an angle goes to R prime, which is a rotation angle operating on R. Now, this angle, the parameter by which the transformation is being given, is physically observable. However, reparametrization that the symmetry that we are currently dealing with is not of this sort. When you take this path, which is parameterized by S, and S goes to S prime, which is a function of S. This is the transformation. S is an internal parameter. The space-time points through which the path is going, if there is a transformation on that, if they change, then that is a physically observable transformation. But S is not directly physically observable, and a transformation on that is not physically observable. So this is not physically observable, not observable. Okay, so in the first case, the observable or the physical quantities in principle depend on theta, but they have a symmetric form because of which they remain unchanged when you change theta. Okay, here in this case, the physical observables cannot depend on change under S going to S prime. So the reason this reparametrization symmetry is present is basically a logical reason, because since it's an internal parametrization, our physics should not depend on that, and therefore that fact should be manifest. To make it manifest, we need to bring in the property of the action that it should remain under reparametrization. And as a result, we are having to introduce new fields, new degrees of freedom, in order to make such a symmetry, such an invariance manifest, for example, lambda in our case. So therefore, any S dependence is basically an artifact of the way we are describing the theory. We could have fixed a particular reparametrization, a particular parametrization of the path, and then could have drawn all the consequences of the theory from that, and then somebody else could use another parametrization completely different parameterization, a valid one, and could have derived all the physical consequences from that theory. And these consequences, these physical consequences, should match. Now, how do you guarantee that that happens? Is that the entire construction of the theory, it should be guaranteed within the kind of construction of the theory, and that is why we made ACE reparameterization manifest and introduced new degrees of freedom, and those degrees of freedom which transform non-trivially under this reparameterization must all be physically equivalent. So that is the idea. So so in this case, therefore, now I'm making this is an example of this is not a physical symmetry in the sense I described here. Such symmetries are in general in general you can call them gauge symmetries. You know, the terminology though is not always used. I mean, gauge symmetry, by gauge symmetry, it is standard to refer to particular type of gauge theories, but here I am using this term, this phrase, in a more general way. For example, I'm calling this also a gauge symmetry. Gauge symmetry means it is a certain internal some ambiguity of the description of the physical theory has been kept in the description in order to make sure that the physical consequences or physical results don't depend on the choice of those internal parameterization. So so let me summarize this, what I tried to say for last few minutes. One is that so these are so this is an example of gauge symmetry in the most generic sense. In gauge symmetry as opposed to physical symmetry. And so gauge symmetries reflect an ambiguity in the description of the theory. So configurations related by such symmetry transformation are physically equivalent. And the impact of that in the present discussion, namely the path integral, is that the physically equivalent configurations should not be overcounted in while doing path integration. We should path integrate only over physically inequivalent configurations. Okay, so this that is reflected in the division of the path integral by the gauge volume. Gauge volume means that when you since the entire thing, this thing is gauge invariant, like under the transformation it remains invariant. If under the transformation you are going from one lambda to another physically equivalent lambda, we should not integrate over both the two configurations. And since this integrand is invariant, the effect of integrating over all the gauge connected configurations will be an overall factor, which can be a divergent factor, and that is the volume of the configurations which are all connected by gauge transformations. We should divide by that volume. If we take this integral to be free, if we freely integrate over all lambdas, there is a amount of lambda configurations which are all physically equivalent, and we are overcounting. This overcounting is not not non-trivial, because for each such gauge equivalent configurations the integrand is same, so it will give you a volume factor, and we should divide by the volume, that corresponding volume. So gauge connected configurations should not be over counted in path integral. Such overcounting produces a volume factor to be called gauge volume. With which the free path integral must be by which the free path integral must be divided. Okay, we shall, in the next slide, we shall see exactly how that has to be done.